that's considering our hurdles that we are going to face in JEE Advanced. So this is the first part of physics. We are basically entering physics, and here we will come to know that there are certain concepts that we need to take care of, like units of physical quantities, their dimensions. Dimensional analysis is a concept that is related to dimensions, and there are concepts like error analysis. So basically, we are going to cover two parts: dimensional analysis, and another part is that error propagation in case of exponential functions, wherever we are having some kind of exponential relation between one or several of physical quantities. So we'll try to study all this using some numericals. So let's start with one. We'll start working with the dimensional analysis, and then we'll go to error analysis. So first, what is dimensional analysis and why do we study it? So dimensional analysis is used for relating many physical quantities and also verifying the formula. So basic parts that you can utilize to explain why dimensional analysis is used and what is its benefits is summarized here. That it helps to check corrections of physical equations to derive relationship between different physical quantities. You can obviously get numericals of this part. However, we will not be discussing numericals on this part. Means you might get some question in which you have to derive various frictional or non-frictional units using dimensional analysis, and this is also used to find the conversion factors or conversion ratio. So let's see what we have here, and I would appreciate a lot if someone tries to solve the question along with me. So here, this is our first question on dimensional analysis, and it is asking for dimensional formula. The quantity here is angular acceleration. So how can we go with it? And can someone suggest a formula with which we can start working on finding the dimensional formula of angular acceleration? So first we can use the definition, but it is always beneficial to go with a strong established formula. So can anyone suggest me? I think someone has already tried and answered it, but I would definitely like to go further explaining this thing. So if you go to the formula, angular acceleration, commonly shown as alpha. I think I have not written it properly. Let's write it. Come on. So alpha is given as the rate of change of angular velocity, and angular velocity is again the rate of change of angular displacement. So you can simply say that this is double differentiation of the angular displacement. So it would be d theta by dt. d theta by dt is angular velocity. So if we differentiate it further, we would be getting angular acceleration. So differentiation of this whole quantity, again with respect to time, or simply we would be saying that its dimension would be something like dimension of theta divided by the dimension of time square. Sorry, I should write it in capital T as we write so, T square. You can obviously go using a unit as well. So if you know the unit of angular acceleration is radian per second square, and you know that radian is a unit of angles, and angles do not have any sorry, the what do we call it, the dimensional formula, the angles do not have a dimensional formula. So we can say that this is nothing but m to the power 0, l to the power 0, t to the power 0, and the times would be simply t square. So that would be getting us m 0 l 0 t inverse square. So here also this is giving the same thing, angle having no dimension. So m0, l0, t0, this t is square. So square and in the denominator gives us inverse square here. So that is what we have as our final dimensional equation here. Sorry, dimensional formula here, not equation. And I have already seen someone has tried to answer it. Yeah, several of them has answered it, and that's a good work. A is the right answer. We can move on to the next one. So dimensional formula for magnetic flux. Magnetic flux, we seldom come across magnetic flux in our general physics formulae, but if you try to locate, you can go through it. So magnetic flux is nothing but the number of magnetic field lines. How would you physically represent it? Number of magnetic field lines through a given surface area. So you can say that this is magnetic field times area. That is the formula. So let's say magnetic field is B. We are using this symbol here. Times area. So rather than writing area as A, let's write it L square. So the dimension of magnetic flux equals to dimension of magnetic field times length square. Now can you relate magnetic field somewhere? You know that magnetic force is on a current carrying conductor. We can find it as a force, magnetic force is equal to I L B, where I is the current through that conductor, L is the length of the conductor, and B is the magnetic field. So if we write it in a different way, taking IL in the denominator on this side, we would be getting B equals to magnetic force divided by I L. So if we write the dimensional equation something here, this would be our dimensional equation. So what is the dimension of force? ml, we know that force is mass into acceleration, and acceleration is meter per second square, rate of change of uh, velocity. So length divided by time square, lt inverse square. So its dimension would be m l t inverse square. We can take it, put it here. We are getting m l t inverse square divided by il. We know that I doesn't have is not considered to be a fundamental quantity while uh, using a dimensional formula. We know, sorry, it is used and it is a dimensional formula, sorry, fundamental quantity, and its dimensional formula, or say dimensional symbol, is a, because of the symbol ampere. So a and l. L is again length. We can cancel it out here. We are getting L cancelled with L. So L will have a 0 exponent over it. I think someone has tried to answer. Let me see. Yes, someone has a doubt. I would definitely want to know what the doubt this person is having. And I'm seeing someone is trying to answer this as well. Let's see what's the answer is. But I'll definitely want to know what is the doubt of this person is. So let's continue it from here. We would be getting m l to the power 0 t inverse square and a inverse. Do we have any of our answer here? And might be I'm doing something wrong here. FB BL square. Okay, I have done one wrong thing here. I forgot to put L here because we were considering magnetic field, but finally we have to find the dimensional formula for magnetic flux. So we'll simply multiply L square here, and our answer would be multiplying L square to that, m L square T inverse square A inverse. And anything that is resembling this dimensional formula is D, and that is the correct answer. And so many of you are correct. Okay, someone is asking magnetic field. Right. Someone was pointing out that I had found the dimensional formula for magnetic field. So we just covered finding the dimensional formula for magnetic flux. So is there any other way, or do we have this only way of finding the dimensional flux? Dimensional formula for magnetic flux. I think we can try one another formula. So let me clear it out and we'll start again. So if you recall electromagnetic induction, you might have remembered that the magnetic flux has something to do with the EMF produced, and that is how it is related. The EMF produced in the conductor or in the loop is equal to the rate of change of the magnetic flux. This can be written in this way: EMF is equal to rate of change of the magnetic flux. So if we write this curved E as the symbol of EMF, our dimensional equation comes out to be phi by d. Now, if we take out t here from here, multiply in the numerator, we would be getting the dimensional formula: dimension of magnetic flux equals to E times T. Now again, EMF is not a fundamental quantity. Can we relate it to fundamental quantities somehow? Well, one thing we can know, that the work done on by a charge is somehow related to EMF. So if a charge Q moves in an EMF through an EMF E and it does a work W, we know that W is related to E times Q. So we can say that E equals W by Q. Yeah. W being the work done. Now, again, W is also not a fundamental quantity, but we can convert it to very easily using force and length. Force times distance is work. So, and we have just discussed the dimensional formula for force, that is ml T inverse square. Now multiply length into it. So force times length gives us work. So this is our dimensional formula for work. And now we have to divide work by charge. And charge is Q. We know that again charge is not a dimensional, fundamental quantity, but current is. So, and we know that charge is equal to current times time. So current multiplied by time, A T. Q equals to A T. A represents ampere current, T represents time. Our whole formula gets converted into M L square T inverse square T T inverse square and T here. So this is for EMF into T gives us magnetic flux. So our magnetic flux, the dimensional formula for magnetic flux would be, let me get a partition here. Yeah. So our magnetic flux would be M L square T inverse cube is we are getting here, but we have times T here. So T inverse square times inverse of A, that is current. So whatever method you use, if you are going the right way, you will get the same answer. Again, D. So I believe someone had a doubt and someone was asking. Okay, so the question is when EMF is equal to magnetic flux. So if the time is 1 second, you can simply say that magnetic flux is equal to EMF, but I don't think this is a standard situation that we ever consider. But obviously, if you're saying that certain for certain time 1 second, the EMF, the change in flux is equal to, it is not equal to flux, but the change in flux for 1 second, the change in flux, if it is given in Weber, the same value would be reflected in EMF, means it would be same volt. If 1 Weber change was uh, experienced in 1 second, you would be getting 1 volt of EMF produced for that time. Okay, let's move on to our next question. I hope that person. Okay, will I be okay? Okay, so let's move on to our next question. This is quite like numerical. You can work it out very easily if you consider each segment separately. So the question is force acting on a particle is given by F equals to A minus X divided by BT, where X is in meters and T is in seconds. The dimension of B is. So here we don't have to confuse this B as a symbol of magnetic field. This is just a random or fictitious quantity. Let's work it out. So we know the dimension of F. We can use it. So let me write this here separately. We don't have anything given about A. So let's try to write this dimensional equation separately. Can we write it as F equals to A by BT minus X by BT? Yeah. So two quantities can be added only and only if the dimension of these are same. So using this we can write our dimensional formula something like this. Means the dimension of this part is equal to the dimension of this part is equal to the dimension of this part. Now if we consider this part, we can find out something relation between F, A and B, but we don't have anything about A. We don't need it. So we can simply rub it out and concentrate on these two parts, relate these two parts here. So let's say this thing. Now we have the dimension of force, we have the dimension of time involved, we have the dimension of X, it's in meters, so it's a length. So what is missing? That's B, right? That's what we have to find out. So dimension of B, this fictitious quantity B, is equal to F times T divided by L. And T is time, so we can write it as capital T in the dimension, divided by X. So the dimension of X is L. And now this is the time. We can simply put the dimensional formula for force, that is ml T inverse square. M L divided by L. So L would be 0. T inverse square times T, simply T inverse. This is what we are getting as a dimensional formula. Or am I wrong? The dimension of B is, okay, so if you are putting L to the power 0, you can ignore this thing, simply strike it off, because if it is not here, anything to the power 0 is 1, so you can put it as 1 MT inverse. So that's our answer. Anybody who have got the right answer? B answer, option B. Yes, I think you have tried and you have reached close, but there was something that you missed. So option is D. Meanwhile, you can try and write why do you think B was the right answer. Okay, and rest of us, let's move on. So now we are going to consider error propagation in case of exponential, or in case of power or exponents. So what are exponents and what are power? You know that. What is error? You might know, you might not know. So error is the calculation. Error calculation is something whenever you commit an error in some measurements of physical quantity, or you say the estimation process, the same error gets reflected in further calculations, and how those errors, 1%, 2%, or even very smaller errors like 0.01%, how that affects the further calculation. This is what is error propagation. So try to understand this thing. You might read these things, you might note these things. We will be using simple one consideration of such problem, and if time permits, we can move on with some more discussion on this. So suppose there are three quantities related in this way. Some quantity Z or Z is equal to a to the power x times b to the power y. Then the error of this quantity Z is related to the errors of a and b in this way. X, which was the exponent of a, would be multiplied to the error here, and y, which was the exponent of b, would multiply with the error of b. And what is b? And what is the error of b here? This is the error, and this is the error actual quantity. So this is called the error fraction. So if x is large, say x is suppose x is 2, then this quantity would be doubled. In an error propagation, the exponents affects this way. Suppose area, you are considering area, and you can calculate the length of a square. So if you are finding 1% error in that calculation of length of that square, one side, suppose length or width, both being the equal. So if area you're going to calculate, you will get an error of 2%, because that you can simply say area A equals to length square. So delta A by A would be 2 times delta L by L. And here I said that if the error in length calculation is 1%, means our length fraction, error fraction for length would be 0.01. That would give length fraction, error fraction of area is 0.02. That means 2% error in area. Similarly, you go on with various types of formula, and suppose you're working on some kind of electromagnetic induction. You have error in form of magnetic field, calculation of magnetic field. Obviously you will have error because you can never be 100% sure, however precise your equipment is. So if you're getting some error with magnetic field, if you're getting some error with the length of coil, so those error will somehow be affecting your final calculation of the EMF. So let's go ahead and discuss one specific question on this. Okay, here is the question. I see that the font is small, so I'll be reading this question. Try to listen to me. The current voltage relation of a diode is given by I being the current, is equal to e to the power 1000 times V by T minus 1 milliampere, where the applied voltage V is in volts and the temperature T is in Kelvin. If a student makes an error measuring 0. plus minus 0.01 volt while measuring the current of 5 milliampere at 30 Kelvin, 300 Kelvin, what will be the error in the value of current in milliampere? So, error measuring for voltage is here, and we need to find the error in the value of current in milliampere. Obviously this value is given in milliampere, so I would like you to try this question alone and then we'll work it out. Okay, so I'll be leaving you for 1 minute and then we will work it out together. Okay, now we'll try to solve it together. But before that, I would like to answer one question that one has asked. How will be able to understand that error has occurred? So every equipment has some kind of error margin. Suppose you are using using a scale, you might have seen that there are markings in that, and however precise you are, you can have you can find that you cannot be as precise as less than 1 millimeter or 1 millimeter, which is the least count. Suppose you are measuring a distance of a length. What you will do, you will put your scale or your tape on that, and you will be able to give the correction as close as your least count. If your least count is smaller, say even smaller than 1 millimeter, you will be getting less error. But if your least count is suppose 1 centimeter, we don't have further breakings into that, further division in your scale, then your error is much larger in that case. So suppose you're using your palm to measure something, 1 palm length, 2 palm length, 3 palm length, something like that. So considering this palm length has a standard unit, can you say that something would be 1/3 of your palm length or 1/4 of your palm length? If something is 1/4 of your palm length, you are not sure that's is it right or not. So in that case, you make an estimate, and with estimates there are errors associated with that. So let's try and solve this question together. Okay, so current voltage relation is given by this. I equal to e to the power 1000 volt by time minus 1 milliampere. It says that while measuring a current of 5 milliampere at 300 Kelvin, we have a error margin of 0.01 volt. So let's try to take out volt out from here using differentiation. So if we derive this whole quantity, so for now, say this is not here, let's remove milliampere part, but remember that this quantity is milliampere. So if we differentiate this whole equation with time, what will be getting, not with time, with voltage V, what would be having? This equation is something like, let's say this is y into e to the power kx, right? If we differentiate y, dy by dt, dy by dx would be e to the power kx times k, right? But can you see the relation here? You can see that k is here, 100 by t part is k, and v is by which we are differentiating, that is the x quantity that is relevant to, and 1 is a constant, so obviously 1 would have 0 differential values. So let's erase what. Okay, so di by dv is equal to e to the power 1000 v by t. Okay, we'll simply write the whole thing here, times 1000 by t, because we are taking whatever is multiplied with v here. And minus 1 would be gone from here. So we know that the value of I is 5 milliampere, right? So value of this part would be 5 plus 1, that is 6 milliampere. So we can simply writing the value of this part as 6 milliampere. Times 100 by t. So, sorry, 1000 by t. So T is the temperature, 300 Kelvin. So obviously if we are considering milliampere and this whole value, we would be getting our voltage in millivolt. So let's remove this part and write Okay, let's forget this part for now. We'll be writing it again. So we know that our difference, or say the error of our voltage is 0.01 V. We'll write that here. Uh, that we are getting as 6 times, yeah, we will be writing di by I, or dv, di being the error of current, and v is being the current of error of the voltage. So we can say that error of di is equal to error of voltage dv times this whole here, and that we are getting as dv is equal to 0 point plus minus 0.01 volt times 6000 by 300, that equals times 20. Let me see if I'm doing it right. I think I might have done something wrong here. Let me try and see what calculation is missing. So the current voltage relation of diode is given by okay, I think I have written one part wrong here. This is V should not be here, because there was the thing has to be converted into the error margin of the current. So that would be simply this whole quantity is in milliampere. Sorry about the whole confusion that I have created. Okay, and 0.01 times 20 is 0.2. So our error would be plus minus 0.2 milliampere. So do we have a right answer that matches the right option? Someone has tried to answer it? Yeah, B, C is correct. Yeah, I've seen several attempts, but sadly none of them is right. So 0.2 milliampere is the right answer. So you can go on and try to solve simple questions like this, and further complication would be using further questions, and complicated question could be solved by simpler concept that we have studied. There's no more complexity for this subject, I hope. But if you get more complex, you can try to break your question in several parts like we did with our dimensional analysis, and we'll be able to solve it. For now, I'm trying to close it here, and we'll meet again in our next classes. For now, goodbye.